Hello and welcome to the lecture Generative AI. In this lecture, we are going to introduce generative AI. Then we try to understand why generative AI is important nowadays. Then we discuss different application of generative AI, and then we conclude this lecture by learning the different models for generative learning. Today we'll start generative AI. As of now, whatever we have discussed, that our deep learning models are basically used for prediction tasks like classification, regression, like that. But in generative AI, we will enter in a bit different application areas where our models will create new or original content like text, images, audio, video, and so on. What it essentially do, it learns some pattern from an existing samples or a set of samples, a large scale data, and then it creates these new samples. So what is the basic idea of these generative models, which essentially creates new content? That given a set of samples, it essentially a data distribution. So you can say that a distribution is given by virtue of a set of samples. So generative models want to or try to create some new samples, and that is very important. The samples what have been given, it is not reconstruct them, rather it create a new samples but that follow the given distribution. That as a whole, I mean very briefly, the generative models do. So foundationally, if we think that these Gen AI models are kind of human-like, creative, kind of problem solving. We are now know a lot of chatbots like ChatGPT, Gemini, like they are functionally generative models. If you say that what are the popular generative models technically, that is generative adversarial network, popularly known as GAN, variational autoencoder, then diffusion models, large language models. These are the examples or emerging generative AI models nowadays. So one important thing, it is very surprising and very important, that generative model is basically unsupervised learning task. We'll see in this course of study that how generative models is actually working. And we see that any typical annotation is not required for this kind of models. Now, the question is very important. Why generative AI models are so important nowadays? Now, in this figure, this is very familiar with us. It is ImageNet challenge. we can see that from 2012 onwards, supervised deep models performing very well. It outperforms most of the conventional machine learning models. And in 2015, ResNet beat the average human efficiency or accuracy. But these supervised models, or we should say deep supervised models, one disadvantage. What is the disadvantage? It requires large annotated dataset. And we also observed that with increase of the dataset size, that we can say larger the dataset means annotated dataset, or more diverse the annotated dataset, better the result or better the accuracy. So what is the problem? The collecting such big and accurately labeled dataset, that means annotation itself, very costly and time consuming job. Most of the time, see, expert annotator are required. If you see in medical imaging, surveillance kind of applications, there we required some expert annotator, which definitely costly and sometimes is not that much available. So there is a data scarcity is always a problem for deep supervised classifier models. So in this scenario, synthetic data generation, which can be done using these our GenAI tools or GenAI models, may be a very good solution. So what we'll see in this lecture, that how generative AI models generate synthetic data, annotated data for this purpose. Now we are going to take a quick look what are the application areas of generative AI models in recent times. So we can see that different sectors like technical, human resource, marketing, sales, and there is a lot of subdomains like supply chain management, e-commerce, financial technology, healthcare, banking, and many more. Definitely there is a lot of areas where this synthetic data generation is a need in recent times, and generative AI tools can be used very popularly in these domains or subdomains of applications. Not only industry application, different research labs required some data set for doing different research activities. For that reason, this synthetic data generation is a very much requirement. Now, for example, if we say that what are the tools or product is very popular nowadays, some image generation tools like DALL-E, video generation tools like Synthesia, NLP based text generation tools is just, but these are just, I take his name. The voice generation tool like Speechify and so on. These are a large list of AI tools or products that have been used hugely in today's research and industry areas. Now, before we go to the technical understanding of generative models, let us have a quick look at the evolution of these models. Definitely from the application viewpoint. Very long back, in 2010, most of us use the autocomplete feature in Google search. That may be a first stepping of GenAI models or kind of GenAI approach to them. A very popular applications or become very popular. In 2013, Deep Boltzmann machine came. That was also a GenAI model. In 2014, Goodfellow et al. Proposed GAN, Generative Adversarial Network, and it became very, very popular for synthetic data generation. Followed by Alexa by Amazon in 2015. Another revolution came in 2019 when OpenAI proposed or invented GPT-2 for NLP text generation. In 2021, the newer version or advanced version of GPT 3.5 come and many more nowadays. Some newer version of GPT, Gemini, and so on. So what we can see that we are now in era of generative AI. Okay. So now we are going to understand what we mean by learning models. So there is two types of learning model. As of now, whatever models we have discussed, they are in principle a discriminative model. What we mean by discriminative models? Are models which learns by a virtue of the way of discriminating. So if you go by definition, the learning by discriminating between two classes of data in a binary classification. So example is classification that a face is fake or real. That this is a very analogical, that when a human, a very small child, learns something, a child always learns by discriminating. That how a bicycle is different than a cow. That a bicycle has two wheels, but cow don't. Something like that. So we learn something by discriminating features of two or multiple objects or events or anything. So that essentially is a discriminative model. But in generative model, learns differently. Rather than understanding the difference between two or more substances or events or objects, they try to model a set of data. It is a bit simplistic. So what essentially do a generative model G is trained on training data X. So this X, a set of samples, a training data samples. From where it comes? It sampled from a true distribution D. That D we don't know, but we know D by virtue of the samples. Okay? Then this model, it produces some data. It may take input from a latent distribution, like a latent space, some random distribution set, and produce some samples. Okay, and that samples, what has been produced by this generative model, let's say it is D bar. So what is the target of generative model? Somehow it creates such samples, new samples, so that this D and D bar should be close. Okay? So if I read out this sentence after this understanding, it basically saying this: a generative model G to be trained on a training sample X sampled from some true distribution D is the one which, given some standard random distribution Z from where it starts, produce a distribution D bar, produce a sample of distribution D bar which is close to D, and according to some closeness distance, a statistical measure or statistical distance measure. So mathematically you can say it starts from some random variables, some maybe some normal or random latent variables, and it basically produces Z of Z. This G is a generator and it generates something which belongs to some D bar, and this D bar, it generates such a way this D bar is close to the D. That is its target. So as a whole, generative models is like this. It is different than discriminative model, where given to distribution, we generally try to understand the decision for classification. How two distribution or two set of samples are different by virtue of knowing this decision boundary for classification case. Okay, with this understanding, we try to understand a bit in depth what is discriminative model is. Now here you can see that is two set of data. One is red and one is green. Now given these two set of data, Unsupervised gate is a annotated data. In discriminative model, we are trying to define or trying to derive this decision boundary. Okay. So what essentially we do? This is basically a two-steps process. First, we extract the features, maybe manual, maybe automatic. That features called discriminative features. The features is what? That is different, that make it different than, or that distinguish between these two datasets, discriminating these two datasets. Like that, what we can say, this is a red and this is a green. So this color is discriminating these two set of data. So this is discriminative features. And then these features are fed to some classifier, maybe support vector machine, maybe neural net, anything, maybe logistic regression. So based on the difference between these two, maybe red or green, maybe real and fake, maybe +1, -1, and so on. So discriminative model as a principle learns through discrimination. And what it learns? It learns this discriminating line, that is popularly known as this decision boundary. So it essentially finds decision boundary between two classes or cluster of data. That is essentially the discriminative model. Now we are going to understand generative learning. So before we start to understand or discuss the generative modeling, let's start some statistical preliminaries. Now first we'll start with density estimation. What do we mean by density estimation? That density estimation means learning the probability distribution of the data. So for example, that there is a samples of data is given. This samples X belongs to that P data X, something like that. So what we want, we learn this data distribution P data of X by virtue of a model. It's a parametric model given by parameter theta, the P theta X, that approximate this two distribution P data. So our model that is want to know or model the density estimation, can say that we want to learn a model, parametric model P theta X, that is equivalent to P theta X. So you can say the maximum likelihood, this is a method of density estimation. So as a whole, that is the major, one of the major understanding to understand the generative model. Because you can see, or we'll see in later slides, that what generative models is basically want to do, that given a model or given a distribution, that is virtue of some samples, we want to generate samples which belongs to that distribution. So what is first required? We required a model that approximate this distribution, so that if you understand this or model this, that approximates some true distribution, then we can sample it from this P theta X, that essentially closer, that newer samples what going to generate, it's somewhat close to that PDT. So that is the essential why we are interested for density estimation. And MLE is one of the, you can say, tool or method for density estimation. Okay. Now we start defining that what is generative modeling. So generative models try to learn a probability distribution of data P of x. Why? So that it can generate new realistic samples. That exactly what we have defined that generative learning or generative modeling. That given a distribution by virtue of a sample of data, we have to learn this probability distribution or at least approximate probability distribution so that we can generate new realistic samples. For example, we can predict next tokens in a language model or create images, audio, etc. Okay, so generative model try to learn the probability distribution of data Px such that it generates new realistic samples, predict next tokens, language models, or create images, audio, etc. And what we can see, some of the general, most of generative models they just trained using maximum likelihood estimation. Maybe explicitly, maybe implicitly, but basically sometimes they use. For example, our language model like ChatGPT. So generative modeling is there's a very naive way. Understand? Works in this way. Let's see what the generative models go bit deeper. So what we have seen, generative models and this density estimation are very kind of tightly coupled and very kind of similar in unsupervised machine learning. Now, why we called it unsupervised? Because there is no need of this kind of typical annotation what is required in supervised learning in this kind of generative models. So what generative models essentially do? It simulates data by explicitly or implicitly estimating the underlying probability density of a data set. That's exactly what we have seen. That we are trying to model to understand a given probability distribution by sample of data. But it is not annotated, only data is given. Okay. So this is very important that it is unsupervised nature. Now, what density estimation do? It try to model a data distribution. That what we have in estimation means learning a probability distribution. So it model a distribution given a samples of p data of this p data. This is the distribution. This is the samples out of this distribution, and we learn a model, that parametric model given by theta with this that approximate this to distribution such that p data is equal to very similar to p data. So that's why we say the density estimation focused on modeling the data distribution. And generative models use this knowledge of modeling this distribution to create new samples with many modern approaches. Sometimes they require that precise density modeling, just for diffusion model normalizing. Sometimes it's not direct modeling is not required. No direct modeling is required in case of GANs where sampling is done, high quality sampling. So generative model is essentially coupled with density estimation. Sometimes they directly used it, or sometimes it's implicitly or just doing the sampling, case of GANs. So what we understand that many generative models are methods of estimating probability densities, either explicitly or implicitly. So now we have some sort of understanding that how generative models works bit statistically. So what is the takeaway message from this is very important slide. First of all, generative models and density estimation are very tightly coupled. They are supervised in nature. The data samples are there, but they are not annotated. So generative models learn simulate data by explicitly or implicitly estimating the underlying probability density, and that is what is density estimation. And by using this knowledge, they create new samples. Knowledge means what? It's data distributions. So they're estimating probability densities either explicitly or implicitly. They means generative models. Okay. Now we bit mathematically, or better to say bit statistically, that let there is a true distribution x, y, that p data of x, y. So a generative learning method learns the parameter theta of a model. It's a parametric model given by this parameter theta. Theta may be many, theta 1, theta 2, something, such that this p theta x comma y can model this. So it becomes very similar. So generative learning is the estimation of the joint probability distribution p of the data. Okay, that is going to. So the joint distribution can be written as p theta of x comma y, that p theta y of p theta x given y, where this is this kind of thing, p of y. So this thing parametric, this theta is a parameter only, is a class prior, and this conditional probability is class conditional density. So we can think through this generative modeling that it essentially model a given distribution. How it model? It essentially model the joint probability distribution, and distribution can be written. So statistical definition, a very simplistic statistical definition of generative models is like. Now we are going to understand the maximum likelihood estimation. This maximum likelihood estimation, or MLE in short, is a method for training models. So what do we mean by training models? That when we are trying to approximate a model, now MLE, what exactly do? You can understand this sentence, that MLE answered the following question. So what are the parameters which make the observed data most probable under my model? Now there is a given model and we try to approximate it by a parametric model. Now we have a parameter theta. So we mathematically choose parameters theta such that it maximizes the likelihood. That is very important to understand. So this theta, we choose such theta or thetas so that this likelihood is going to be maximized. So it basically say what? That if we go sample by sample, it is basically the multiplications of probability values of individual samples. So I is equal to n is number of samples, and p of theta, that is the parametric model of these particular samples. So in practice, we generally maximize the log likelihood because it's easier to compute. So this, under this log, this multiplicative become additive, so it's log of p of I given theta. So that is one of the major tools or way training the models. So Emily chooses the density that makes the observed data most. So that is the basic idea, very simplistic idea of maximum likelihood estimation, and that has been used by some of our generative models for density estimation. Okay, now these three terms what we have understood, we are discussing or we try to understand the generative models and this density estimation. In generative models is basically implicitly or explicitly try to estimate this density, and MLE is one of the training method or tools for the density estimation. So when we maximize the likelihood, we are adjusting this p theta of xi. So those theta we are going to choose that it assigns, our model assigns high probability where the data occurs and low probability elsewhere. That is the likelihood means that is better to say that is called the maximizing the likelihood. So where this data occurs, we put higher probability there, and where the data is scarce or sparse, we put a low probability there. So if we put in expectation formation, so that the max of theta, we choose those theta, so that this expectation where x belongs to this true distribution, p data is log of p theta x. That is basically this. So this is equivalent to minimizing our KL evidence. That distance between this, or you can say that these two distribution is by p data by p theta. So that we can say the MLE is a KL, Ebel-Kullback based density estimation. And generative models like variational autoencoders, autoregressive models, these normalizing flows often use this maximum likelihood estimation to perform or to estimate or to the density estimation. So that is very important to understand the naive understanding of generative model, where it essentially explicitly or implicitly do the density estimation, and MLE is one tool that is a KL based density estimation. What these popular models generally do. Okay, let's try to understand why it is called generative now. We have now understood what this generative model is doing. Now what we have learned? We have learned this joint distribution by virtue of our this parametric model. Maybe using MLE, we explicitly or implicitly. Now once we joint distribution is learned, we can generate labels that why this belongs to this distribution. We can generate data, this p theta of this x belongs to this p theta x, y, and generate unconditional samples. Okay, that p theta of x. Now we can generate it. We are in a position to now generate labels, data, unconditional samples. Thus, this model is called the data generating process. That's why it's called generative modeling under this generative learning paradigm. Okay. Now take example. The language model is a very important generative model. What it essentially do? It's a basically autoregressive model that based on these previous words, that let I am a good boy, this. So if I say I am a, so these previous words see, and to going to generate the next word, good. That is we going to understand or going to predict the next word given the previous words. So how these models are being trained, this language model? The model sees the real sentences. So when it sees the real sentences, then they understand that I am a good boy. This is a sentence. And after I am is come. After I am, a is come. After I am a, good is coming. After I am a good boy is coming. So by this it learns how to predict the next word. So we adjust parameters to maximize the probability of the correct next word. And this is exactly the MLE. What MLE is basically said, that you choose parameter theta that maximize the likelihood. If you know the likelihood that the previous words in our example, we can learn how to choose theta to get the next correct word. So this is exactly the maximum likelihood estimation. So training objective becomes now this. We have to find out xt, where this xt is the next word, and before that, if this is a first 2, 1, 2, 3, 4 these words, so x and these previous words, that's less than t, it is given, and parameters are theta and this log likelihood. So we choose the theta in such a way that is maximized. So simplistically, if we say, it increases the probability of real data. This is a very typical example of a generative modeling, where they use the maximum likelihood estimation, by which maximize the probability of the correct next word given the previous words. Okay. So, in this lecture, what we have understood, first we introduce generative AI. What is the definition of generative AI? Then what are the application and why generative AI is important? Then we try to understand the learning models by understanding some statistical preliminaries like density estimation, maximum likelihood estimation, and then we see an example of this language modeling. In the next, we continue this is generative modeling, how the generative models actually being used, more visual. Thank you.